Okay, now we're going to take a look at linear approximation. You can see we have this red curve, and then you can see we have this blue tangent line. This is the point where the tangent line touches the curve. What we're going to do is we're going to create the equation of this tangent line, and then we're going to plug into the equation of the tangent line in order to estimate the real value on the curve. Now, as long as you're close to the point of tangency, your estimate is going to be pretty close to the real value on the curve. But I want you to notice the further away you get, the worse your estimate is. You can see the further away I get, the worse my estimate is. So in order for your approximation to be close, your x value has to be close to the point of tangency. Okay, we already know how to do the equation of a tangent line. So what we're going to do is we're just going to do that again. We're going to get the equation of this tangent line, and then we're going to plug in a value. So here's an example. If we plug in this x value, our answer is going to be this one up here. You'll notice that's more than the real value is supposed to be. So we're going to have an over approximation. But again, this is just an approximation. Because this x value is close to the x value where your tangent line touches the graph, our estimate is going to be pretty close to the real value. You cannot approximate the value of a curve if your x value is too far away from the point of tangency. In other words, we cannot use the tangent line to approximate the curve over here. You can see how bad our estimate would be. So you have to be close to the point of tangency. Doesn't matter if you're on the left side or the right side. Okay, for this example, we're going to estimate the square root of 9.1. We're going to do it using tangent line approximation. Okay, you can see right here that we have the square root of x function. And then the blue line is the tangent line, but it goes through the point 9, 3. So for this example, our function is going to be the square root of x. We're choosing an easy value that we can plug in, but that's also close to 9.1. So we're going to choose a specific value of x equals 9. Remember, your tangent line has to be close to the x value you're looking for. We want to estimate the square root of 9.1, and we know what the square root of 9 is. It's 3. So we're choosing a value that's easy and that we know, but that's also close to 9.1. Okay, so what we're going to do for this example is we're going to find the equation of this tangent line, and then we're going to plug in 9.1 into the equation of that tangent line. The answer that we get will be a little bit more than the real value of the square root of 9.1. Now, you could probably see that easily over here. If you plug a value into the equation of that line, it's a little bit higher than the real value when you plug it into the square root function. And that continues to happen the closer and closer you get to x equals 9. But when you get really close to x equals 9, the equation of the tangent line and the equation of the square root function are almost at the same height. So we would expect an answer that was almost the same. Okay, let's get rid of this graph and let's do this problem. Okay, so what we're going to do first is come up with the equation of the tangent line. If we choose the function the square root of x, we can get our point, because when x is 9, we get that y of 9 is the square root of 9, and that's just 3. Remember, this is a square root function. It's not a real square root. So that gives us a point. When you plug in x equals 9, you get y equals 3. Now remember, our function is the square root of x. To do the derivative, we could rewrite it as a power of 1/2. Or you can just remember that the derivative of the square root of x is going to be 1 over 2 root x. Again, you could do the derivative by doing the power rule if you wanted, where the 1/2 comes down and the new power would be 1 less. So the new power would be negative 1/2. Okay, again, we need the equation of the tangent line at this point. So since we have the point, we really just need the slope. So we're looking for the slope when x is 9. This is the slope for any value of x. So the slope when x is 9 is going to be 1 over 2 root 9. So we get 1 over 6 for the slope. So now we can find the equation of that blue tangent line. Equation of the line will be y minus 3 equals the slope, and then x minus 9. Okay, we are going to solve it for y, but I'm just going to add the 3 to both sides and that's it. You'll see why in a second. Now this is the equation of the tangent line, But we're going to use this equation to approximate the curve. Remember, the curve was the square root of x function. So what I'm going to do is I'm going to say, well, y is approximately equal to this line right here, as long as x is close to 9. So that's our tangent line approximation. But remember what we want to do, we want to plug into the equation of that line to estimate the curve when x is 9.1. So again, we're trying to approximate the square root of 9.1. Here's the square root function. When x is 9, we have a tangent line. So again, if we plug into the tangent line when x is 9.1, you can see the real value is actually a little bit lower than the value that we're going to get. The value that we're going to get is going to be on that line, and that's going to be a little bit higher than the value on the curve. Okay, let's plug in our value. Now let's simplify. And we can rewrite 0.1 as 1/10. And 1 over 6 times 1 over 10 is 1 over 60. Okay, so this is the answer that we got by plugging into the equation of the line. Okay, remember this point right here is when x is 9. The estimate that we just got on the right side over there is when x is 9.1. So it's going to be on the tangent line, so it'll be a little bit higher than the real value. So the real value on the square root function is going to be a little bit lower. Now let's go ahead and compare those two values to see how close our estimate was. We do expect our estimate to be a little bit higher than the real value. Okay, we'll use our TI-89 simulator. We'll just type in the answers. Okay, you can see our estimate is 3.01667. The real value is 3.01662. So you can see that our estimate was accurate up to 4 decimals of accuracy. That's a pretty good estimate. Okay, I also want to point out that our estimate ended in a 7, where the real value ended in a 2. So our estimate was a little bit more as we expected. Okay, this is a much simpler example. They're just asking us to find the linear approximation. In other words, find the equation of the tangent line. Okay, and we want us to do it near x equals 4. The function is x squared, so when we plug in a 4, we get 4 squared, which is 16. So we already have our point. It's going to be 4, 16. Since our function is just x squared, the derivative is going to be 2x. Now this is the derivative for any value of x. Our x value is 4. So when we plug in a 4, we get 8. That's going to be our slope. So our point is 416. Our slope is 8. I'm going to use the equation of a line. We'll go ahead and solve it for y. And since we're using this line to estimate the curve, we're going to change it to approximately equal to, as long as x is near 4. And that's it. That's the equation of our tangent line. So that would be considered the linear approximation for the function y equals x squared near x equals 4. Now we're trying to estimate this function for small values of h. Now what would be a small value of h? Well, maybe 0. Right? So we're going to say near 0. What throws off a lot of people on this question is that it doesn't have an x, it has an h. Okay, again, we're going to come up with the equation of our tangent line. We're going to use an h value of 0. It's kind of like your x value. Our function is going to be square root of 9 plus h. It's kind of like 9 plus x. When you plug in 0, you get 3. Remember the rule for the derivative of the square root of x? It would be 1 over 2 root x. We don't have an x. We have a 9 plus h. So we're going to have to do the derivative of 9 plus h. And that's just going to be a 1. So we don't get anything extra from the chain rule. But again, we're trying to do the equation of a line. We already have the point. So now we just need the slope. We just found the slope for any value of h. So when h is 0, we get 1 over 6. So our point is going to be 0, 3. And our slope is going to be 1 over 6. Equation of a line. Again, we normally have an x here. So don't get thrown off. Instead of an x, we're using an h. We're going to add 3 to both sides. And again, because this line is approximating this curve, we're going to use the same name as the curve, and then we're going to put approximately equal to. And that's it. That's the equation of our tangent line. And again, we're saying that the answer that we get by plugging into the equation of this tangent line is very similar to the answer that we get when we plug into the real curve, as long as we're near 0. Okay, this one's going to be very similar to all the other ones that we just did. We're going to use the square root of x for our function. We're going to use an easy value that we know that's near 24, so we know the square root of 25. So our x value is going to be 25. When we plug a 25 into our square root function, we get 5. So that's our point. We've already done this one a couple times. The slope is going to be the derivative for square root of x, which is 1 over 2 root x. Now that's the derivative for any value of x. So when x is 25, our derivative is going to be 1 over 10. So that's our slope, 1 over 10. Our point is right here. Equation of our tangent line. We're going to solve for y by adding 5 to both sides. Okay, so we have our tangent line here, and that tangent line is going to approximate our function. Our function was the square root of x. So since it's an approximation, we're going to want to put it approximately equal to right here. Okay, and this line approximates the curve as long as x is near 25. Now the whole point of this question is, how do you write your final answer? So let's plug in this weird value now of 24. And we can simplify. We get a negative 1 in here. And look at the question. It wants to know how much less than 5 is the square root of 24. So I'm going to move this 1 over 10 to the other side. So now we have 5 minus 1 over 10. We want to know how much less than 5 is that. Well, that's pretty easy. It's just 1/10 less than 5. So the answer to the question at the top is 1 over 10. So the square root of 24 is approximately 1/10 less than the square root of 25. We're saying approximately because we used a tangent line to approximate it. Okay, this is kind of a weird one. We have our curve. The 0 is where you cross the x-axis, so that'd be about right here. Then we have our tangent line, trying to exaggerate it a little bit. The 0 for the tangent line is over here. So the real 0 is the point in red. Our estimate of the 0 using the tangent line would be in blue. Now if you look at the graph over here, those 2 points are actually a lot closer. But again, I'm just trying to explain stuff here. So since we're using the equation of the tangent line to approximate the 0, we just need to find the equation of the tangent line and then set it equal to 0. And that'll be our answer. Here they're giving us the point, 3, 1. That's this point right here. They're telling us the slope when x is 3 is equal to negative 2. So if you have a point and you have a slope, you can find the equation of the tangent line pretty easily. Let's solve it for y. We add 1 to both sides, and that would give us a 7. So that's the equation of our tangent line. Normally, we would plug into the value of x. But here, they're just trying to do something different. They're trying to use that equation of a tangent line to estimate the 0. Okay, so we're just going to set it equal to 0 and solve. You can add 2x to both sides, and then divide by 2. Okay, I always like to put the x first, so we'll put x equals 3.5. You can see that the real 0 for that curve is a little bit less than 3.5. Okay, this last one's just kind of a quick, easy one. They give you the point, and you just have to figure out the slope by looking at the graph. This is the graph of the slope. This is the graph of the derivative. So when x is 5, you can see the y value is 2. So that means the slope is 2 when x is 5. So when x is 5, the slope is 2. And that's it. That's the only different thing about this problem. Other than introducing the graph to find the slope, this is just going to be the same as any tangent line problem. How do you do the equation of a tangent line? Well, it's just the equation of a line. You just plug in the point and the slope. Get y minus 11 equals m, and then x minus 5. You can add 11 to both sides. You can combine the minus 10 and the plus 11. And that's it. That's the equation of your tangent line. Again, sometimes they call it local linearization, but it's just the equation of your tangent line. Again, this tangent line is trying to approximate a function called f. So we're saying f is approximately equal to this line. So what I want to do is I want to name my tangent line f, not y. Let's fix that. Okay, there we go. So this means that the actual function is approximately equal to this tangent line as long as x is near 5. And that's it.